All right, now let's take a look at something even more useful, combining conservation laws together. So in any collision, we can use conservation of momentum, right? And we can also use the work energy theorem or conservation of energy when things are moving, from one place to another. So we can combine these laws together and use different conservation laws for different segments of our exercise, right, or problem, to kind of solve more complicated problems. So that's what we have in this exercise here. So we have a bullet being shot into a block, which is on a horizontal surface. This surface is not frictionless, has some friction, coefficient of kinetic friction is 0.2. The bullet is stuck in the block, so we have the bullet remaining embedded in the block. This means we have a perfectly inelastic collision, and then the block, after the bullet gets embedded in, it slides 0.23 meters along the surface, and so we're going to find out the initial speed. This is sort of like just ballistics analysis. We have shoot a bullet into a block. We know the mass of the bullet, mass of the block. Based on how far the block travels, we know how fast the bullet was going. Or we could use this obviously like in measuring skid marks at a car slamming on its brakes, and measuring the skid marks, we can find out how fast it was traveling. So similar type things. This is pretty useful analysis techniques. So let's just write out everything that we have given. So I'll establish a coordinate system first. I'm going to need that at least during my conservation of momentum. And there's a surface along here, horizontal surface, not frictionless. There's a coefficient of kinetic friction equal to 0.2. And there's this bullet shot into a block, I'll call it a crate, and the mass of the bullet is 5 grams, so 0.005 kilograms. The crate here, mass of the crate, is equal to 1.20 kilograms. It says that the crate is resting on the surface, so the initial velocity of the crate, VC initial, is equal to 0. And then it slides over here. It's shot in, and it ends up over here later on. And the bullet is embedded in here. So there's the bullet stuck inside the block, and it's going to end up at rest, right? So we have here this final velocity of both the bullet and the block is equal to 0, or both the bullet and the crate. And they would have a combined mass. This is going to be equal to 1.205 kilograms because it's the crate and the bullet now. And it slides before coming to rest. We know that it slides a distance of 0.23 meters. Is how far it travels before it comes to rest. And the question is, how fast is this going? What is the initial velocity of the bullet? Well, what we can do is we can say, all right, during this bullet going into the block, I can use conservation of momentum, right? But I need to know something about the velocities, right? I'm going to need to know the velocity of this after the collision if I'm going to find anything about this, right? So we'll kind of work this backwards. We can get some information about the speed of the block based on how far it traveled before it came to rest over here, right? So instead of having just kind of initial and final, when we started out with kinematics, we had there was V naught and V final, right? And then with momentum, we had before and after. But when we combine things together, it might be that our final condition for one portion is the initial condition for another. Like, after the collision ends, the work energy theorem will start. And so instead of using initial and final, I think it's probably easier to label things like point 1, point 2, point 3, etc., which we saw some of that when we did energy analysis. So let's say that point 3 over here is when it comes to rest. And point 2 will be immediately after the collision. This will be when the block and the bullet are moving together. And we're going to assume that the collision is instantaneous. And point 1 will be before the collision. So let's just write all these out. So 1 is before collision. 2 is after the collision, immediately after the collision. Basically so that delta t is equal to 0. And 3 will be after the bullet, the bullet and crate stop. Okay. And the strategy here will be to work backwards. We'll use the work energy theorem backwards from 3 to 2. So 3 to 2 or 2 to 3 work energy theorem. And then from 2 to 1, we'll use conservation of linear momentum. Okay, so let's go backwards then. So from 3 to 2 or 2 to 3, we will have the work done by friction will be equal to the change in kinetic energy, because this is the only form of energy that we have, right? Kinetic energy. There's no change in height, so no change in gravitational potential, and also no springs. So we look at this quickly, with a free body diagram. We have there's a frictional force back like this. If it's on a level surface, we have our weight going down here, the normal force going up. The normal force will be equal to the weight on this level surface. And so the work done by friction will be the frictional force times this displacement here. And so we have the work done by friction is, and this is negative, obviously. The work done by friction is always negative, but based on our sign convention, the force is negative, but displacement is positive. And so I'll write this out as negative F times displacement is equal to 1/2 mass times the speed at point 3 squared minus 1/2 mass times the speed at point 2 squared, right? This is the kinetic energy at 3, and this is the kinetic energy at 2. So it's the change in kinetic energy from 2 to 3. So this frictional force, this is negative mu k mg. The normal force was mg in this case. And this is going to be equal to then, I can factor out the 1/2 m. And actually V3, even simpler here, because it came to rest, V3 was equal to 0, right? And so this is actually just equal to negative 1/2 m V2 squared. So the mass was the same in both cases because the bullet was embedded in the block at point 2 as well as point 3. And so this is the work done. Remember, this is the work done from 2 to 3. So the mass was the mass of the bullet and block together. So mass cancels out here. And we end up with V2. These negatives also cancel out. And we end up with V2 is the square root of 2 mu k gs, right? So plus or minus, but we know that it's going in the positive direction. So the magnitude of v2 is equal to 0.949 meters per second. Where this s is how far it traveled, right? So that was 0.23 meters. And g is the same, and mu k was the 0.2. So this v2, though, is really important to note what this v2 is. This is the speed right at point 2, which we called 2 is immediately after the collision. It is the initial speed when we use the work energy theorem, so it's like, yeah, the initial speed of the bullet and crate together, but it's the final speed after the conservation of momentum. So this is point 2 is like initial for one part, but final for the other part, and this is why I call it point 2 instead of initial and final. Okay, so this v2 is this is speed of bullet and block immediately after collision. Okay, so now I can use, now that we have that speed, we can use conservation of momentum from 1 to 2. So from 1 to 2, conservation of linear momentum. So then we have I guess the momentum at 1, write it out this way. The momentum of the system at 1 is equal to the momentum of the system at 2. So at point 1, because the crate was not moving initially, then we have the total momentum of the system, right? This was the initial velocity of the crate was equal to 0. And so the momentum of the system was just the momentum of the bullet originally, right? So this is basically the mass of the bullet times the initial velocity of the bullet is equal to the mass of the bullet plus crate times the velocity of the bullet plus crate, right? But this is v2. And this we know because we know both of their individual masses, right? And so we end up here with I'll write it all out like this, 0.005 times VB initial is equal to 1.205 times 0.949, and we can solve for the initial velocity of the bullet. VB initial is equal to 229 meters per second. Is how fast it's going, which is, I guess, it's fairly reasonable for a bullet. It's very fast, but bullets travel very quickly. So there's an example combining conservation laws together, and I think the most straightforward way to go about it is to label points like 1, 2, 3, 4, etc. Instead of like initial and final.